Hello students, I am Dr. Shweta Sharma from ABES Engineering College, Ghaziabad. In this lecture, I'll be discussing about the UV visible spectroscopy. The content which I'll share in this lecture is about the brief introduction of spectroscopy, principle of UV visible spectroscopy, that is Beer-Lambert's law, UV visible spectroscopy terms like chromophore, oxochrome, absorption shifts, and different intensity shifts. I will discuss about the instrumentation of UV visible spectroscopy, applications of UV visible spectroscopy, and some numericals related to Beer-Lambert's law. So first of all, what is spectroscopy? Spectroscopy is the science in which we study about the interaction of electromagnetic radiations with the matter. What are electromagnetic radiations? Electromagnetic radiations are those radiations which consist of electric field and magnetic field perpendicular to each other and perpendicular to the direction of propagation, moving at a speed of light. When these radiations interact with matter, we study it in the form of spectroscopy. So basically, spectroscopy means study of spectrum, in which we study about the different types of spectrum when these electromagnetic radiations interact with the matter. UV visible spectroscopy means we are discussing the ultraviolet and visible part of the spectrum. Spectrum, if we say, means it is the array of radiations. If I'll talk about the electromagnetic radiations, so spectrum is array of electromagnetic radiations in the increasing or in the order of increasing wavelength or decreasing frequency. As we move from gamma radiations to long-range radio waves, frequency of radiation decreases, means energy of these radiation decrease from gamma radiations to radio wave, and wavelength increases. When we talk about the UV visible spectroscopy, we are concerned about this part of the spectrum, UV and visible part of the spectrum. UV radiations correspond to 400 nanometer to 200 nanometer to 400 nanometer, and visible region we are studying expand from 400 nanometer to 800 nanometer. This visible region 400 nanometer to 800 nanometer consists of VIBGYOR, that is violet, indigo, blue, green, yellow, orange and red color. This is the region which expands from 400 nanometer to 800 nanometer. So in this UV visible spectroscopy, we are concerned with the 200 nanometer radiation to 800 nanometer radiation. Principle of UV visible spectroscopy is Beer-Lambert's law. Beer-Lambert's law says that when there is any medium and when light is allowed to pass through this medium, this is the light or any monochromatic light is allowed to pass through this medium, then this medium absorbs some of the light and remaining light will be passed through it. The light absorbed by the medium is known as absorbance. This is the absorbance of the medium. Absorbance depends upon the path length, that is, the distance traveled by the light, and it depends upon the concentration of the medium. Whatever is the concentration of this medium. So, if I'll say Beer-Lambert's law is absorbance, which is directly proportional to the concentration of the medium, and it depends on the path length. This is the distance traveled by light. I naught is the initial or incident intensity of the radiation, and I is the intensity of the transmitted radiation. I naught is greater than I, or we can say I is less than I. Intensity decreased because light has been absorbed by the medium. Therefore, transmitted light has lesser intensity as compared to the incident radiation. If I express it, absorbance is epsilon Cl. This epsilon is the constant of proportionality of Beer-Lambert's law, and it is known as absorptivity. It is called as absorptivity of the medium when we express the concentration in gram per liter. This is absorptivity. When we express the concentration in moles per liter, this constant is known as molar absorptivity. This is molar absorptivity when concentration is expressed in moles per liter. In this case, Beer-Lambert's law is expressed as A is equal to epsilon Cl when concentration is in gram per liter. When we express the concentration in moles per liter, it is epsilon m Cl when concentration is in moles per liter. There is another name for this Beer-Lambert's law constant. It is also known as extinction coefficient. When concentration is in moles per liter, it is also known as extinction coefficient, and it is also known as molar absorptivity or molar extinction coefficient. Molar extinction coefficient. So these are the names of the constant of molar Beer-Lambert's law constant. So if I'll relate the statement of Beer-Lambert's law with the mathematical statement, it is that absorbance of the light for the given material is directly proportional to the sample path length. This sample path length is the distance traveled by light, and it depends on the concentration of the sample. We can also express Beer-Lambert's law in terms of transmittance. So first of all, what is transmittance? Transmittance is it is the ratio of incident radiation and transmitted radiation. So transmittance is I upon I naught. Percent transmittance is I upon I naught into 100. If transmittance and absorbance is related, then we can relate absorbance is equal to log 1 by T. It means absorbance is equal to log of I naught upon I. This is the relationship between absorbance and transmittance of the medium. So, what are electronic transitions in UV visible spectroscopy? UV visible spectroscopy is also known as electronic spectroscopy. It is also given the name electronic spectroscopy. because whenever any medium absorb the UV radiation, it show electronic transition. That's why this spectroscopy is also known as electronic spectroscopy. The transitions are sigma electron to sigma antibonding. So this transition is basically exhibited by all saturated hydrocarbons or all saturated compounds where electron absorb energy and undergo sigma to sigma antibonding transition. If we have pi electrons in unsaturated molecules, then these pi electrons absorb energy and move to pi antibonding orbital. This transition is pi to pi antibonding transition. Next, we have non-bonding electrons, which means lone pair. Lone pair can show two transitions. They can absorb energy and move to sigma antibonding transition, and when they absorb energy, they can move to pi antibonding transition. So basically, we have four types of transitions in UV visible spectroscopy on absorption of UV radiation or visible radiations by the concerned electrons. If sigma electron can absorb energy, it will undergo sigma to sigma anti-bonding transition. This is the highest energy transition. And if pi electron absorb energy, it will undergo pi to pi anti-bonding transition. Then we have non-bonding to sigma anti-bonding transition. Then we have pi bonding to pi anti-bonding transition, and then non-bonding to pi anti-bonding transition. This is the sequence of energy of these transitions. So basically, if we see that sigma to sigma anti-bonding transition is very high energy transition, and usually these transitions are exhibited by saturated compounds or saturated hydrocarbons, and they fall in the range of 125 nanometer around. It fall in the range of 125 nanometer, and this is basically the UV region. Then we have non-bonding to sigma anti-bonding transition. These transitions are exhibited by the compounds which contain heteroatoms like oxygen, sulfur and nitrogen having lone pair, and these transitions fall in the range of 150 nanometer to 250 nanometer. Again, this region or this value corresponds to UV region range. So these are high energy transitions which fall in ultraviolet region or UV region. Then we have pi to pi anti-bonding transition. These transitions are exhibited by compounds which have unsaturation in them, having double bonds or triple bond in them, unsaturation, and they fall in the range of around 170 nanometer to 205 nanometer. Then we have non-bonding to pi anti-bonding transitions. These transitions are exhibited by the heteroatom bonds like nitrogen-oxygen bond, carbonyl bond, carbon and sulfur bonds. These are extremely low energy transitions and they correspond to the low energy values. So these are the types of electronic transitions which are exhibited in the UV visible spectroscopy when molecules absorb radiations or absorb UV visible light. Next is chromophore. Chromophore is a Greek word which comprises of the two words chroma and phore. Chromophore literally means color carrier. This is the literal meaning, but the technical meaning is slightly different from the literal meaning. Technical meaning, or technically it is defined as any isolated covalently bonded group that show characteristic absorption in the UV or the visible region, irrespective of the fact whether color is produced or not. So, if we say simplify this, chromophore is any group which show UV visible light absorption, and it is not necessary that after absorption of this light, it will show color. So color production is not compulsory, it is not necessary, but if any molecule isolated covalently bonded group is showing UV visible light absorption, it will be defined as chromophore. We have two types of chromophore. Firstly, those chromophore which contain pi electrons. These chromophores show pi to pi antibonding transition as they contain pi electrons. This transition is shown by those molecules which have unsaturation in them. For example, ethylene, acetylene. These are unsaturated molecules and they show pi to pi antibonding transition. Second chromophore is those which contain non-bonding electrons and pi electrons. They show two types of transition, pi to pi antibonding transition, as well as they show non-bonding to pi antibonding transition. These chromophore are those molecules which contain carbon with unsaturation with heteroatom, like carbonyls, like carbon with a sulfur. So these are chromophore which contain non-bonding and pi antibonding transitions. So these are the two types of chromophores. Oxochrome. Oxochrome is basically a color enhancing group. The purpose of the oxochrome or the function of the oxochrome is to enhance the absorption pattern of chromophore. It helps the chromophore to enhance its absorption pattern towards the higher wavelength or towards a longer wavelength of spectrum, means it helps the chromophore to shift its absorption maxima towards the red region of spectrum. Oxochrome by itself do not act as chromophore, but it helps the chromophore to enhance its lambda max or its absorption maxima towards the longer wavelength. It helps the chromophore to enhance its lambda max or absorption maxima towards the longer wavelength or towards the red region of spectrum. These groups like OH, NH group, SH groups, these groups are examples of oxochromes. They help the chromophore to shift the absorption pattern towards a longer wave. They help the chromophore to shift the absorption pattern toward the longer wavelength with the help of lone pair associated with them. They help the chromophore to extend the conjugation and shift the absorption maxima towards the longer wavelength. So, these lone pair helps in conjugation. Absorption shift. We have two types of absorption shift. First is redshift. We also call it as bathochromic shift. Redshift or bathochromic shift means it is a shift of absorption maxima towards the longer wavelength of a spectrum due to increase in conjugation of the molecule. So what happened in the redshift? In the redshift, we have this is the pattern of a molecule, absorption pattern. This is percent absorption, and this is the lambda max of the molecule. This is lambda max, and x-axis showing the wavelength. This is the lambda max of the molecule or the absorption maxima of any molecule. Suppose in this molecule, conjugation is introduced or conjugation enhanced. So what happened due to enhanced conjugation? This molecule will show absorption maxima at the longer wavelength or at the higher wavelength. So in the bathochromic shift or redshift, what happened? The lambda max shifts towards the longer wavelength, or this is known as redshift. Lambda max was earlier when the conjugation was less. This is the absorption maxima when molecule has enhanced conjugation. This is redshift, means shift of absorption maxima towards the longer wavelength. For example, in this molecule, lambda max is 175 nanometer, and when there is conjugation, molecule has enhanced lambda max at 217 nanometer. So due to conjugation, absorption maxima has shifted towards a longer wavelength. This is bathochromic shift or redshift. Next is hypsochromic shift or blue shift. This is the shift of absorption maxima towards the shorter wavelength due to decrease in conjugation, of the molecule. So here what happened? This is the absorption maxima of the molecule or absorption pattern, and this is the lambda max. Suppose in this molecule, conjugation is decreased. Now, the lambda max is shifted towards the shorter wavelength. This is now lambda max, percent absorbance on the y-axis, wavelength on the x-axis. This is blue shift. Earlier, when the conjugation was more or there was decrease in conjugation, lambda max shift from higher wavelength towards shorter wavelength. This is blue shift. And blue shift occurs when there is decrease in conjugation of the molecule. For example, this is aniline molecule. Aniline show lambda max at 280 nanometer. Anilium ion show absorption maxima. This is anilium ion, show absorption maxima at 203 nanometer. This is the shift of absorption maxima towards lower wavelength or shorter wavelength, and this is known as blue shift. Next is intensity shift. Hyperchromic shift is defined as increase in the intensity of absorption due to increase in conjugation or electron density. Suppose we have a molecule Like this is pyridine. Pyridine show absorption of 2750. This is the intensity of absorption of pyridine. And here we have methylpyridine. In case of methylpyridine, intensity of absorption is more as compared to simple pyridine. This more absorption in case of methylpyridine is due to the hyperconjugation effect of the methyl group, which is imparting more electron density to the benzene ring or to the aromatic system. Due to this, more absorption of radiation takes place in case of methylpyridine. So this more absorption is due to increased electron density. This is increased electron density in the methylpyridine. This is hyperchromic shift when intensity of absorption is increased. So what happened? This is the absorption and this is wavelength. In case of pyridine, this is the absorption pattern. And in case of methylpyridine, this is the absorption. Now, the molecule is absorbing more radiation. This is or increase in absorption, increase in intensity. This is hyperconjugation. Hypochromic shift. Hypochromic shift is decrease in the intensity of absorption due to reduced conjugation or electron density. What is in hypochromic? Hypochromic is when we have a molecule. This is the absorption pattern of the molecule. This is wavelength. Suppose in the molecule, electron density is reduced. Due to this, now the molecule is absorbing less radiation or intensity of absorption is decreased. This decrease in intensity of absorption is due to the decreased electron density on the molecule. For example, in case of benzene, intensity of absorption is this 11160, and in case of benzoate ion, this is benzoate ion. In case of benzoate ion, intensity of absorption is 8700. This value is decreased because of decreased electron density on the benzene ring due to minus I effect of the benzoate ion or due to carboxylate ion, due to minus I effect of the carboxylate ion. So this is hypochromic shift or decrease in intensity of absorption due to decreased electron density or reduced conjugation. So if we summarize all the absorption and intensity shift, we can say that red shift is defined when lambda max shifts towards the red region of a spectrum or towards the longer wavelength. Blue shift occurs or hypsochromic shift occurs when lambda max shifts toward the shorter wavelength. This is known as blue shift. Hyperchromic shift is the increase in intensity of absorption, and hypochromic shift is decrease in the intensity of absorption. Now let's take some questions of Beer-Lambert's law. A compound having concentration 10 raised to the power minus 3 gram per liter give absorbance 0.20 at a monochromatic wavelength of 520 nanometer using cell of 1 centimeter. Calculate the absorptivity and molar absorptivity value. Molecular weight of the compound is given 400. So according to Beer-Lambert's law, absorbance is equal to epsilon Cl. We have to calculate absorptivity, which is expressed as ABES upon Cl. Absorbance is given as 0.20. Concentration is 10 raised to the power minus 3 gram per liter, and path length, that is cell, is 1 centimeter long. This is epsilon A upon Cl. This, when you calculate, this is 200 liter gram inverse centimeter inverse. This is the absorptivity or extinction coefficient. Molar absorptivity, to calculate molar absorptivity, we will take formula absorbance is equal to epsilon mCl, where concentration is given in moles. So molar absorptivity is A upon Cl. This concentration is in moles. Absorptivity is 0.20 and concentration is 10 raised to the power minus 3 divided by the molecular weight 400. This is mole per liter and L is 1 centimeter. This is 8 into 10 raised to the power 4 liter mole inverse centimeter inverse. So in this way, we have calculated molar absorptivity and absorptivity for the given solution at 520 nanometer wavelength. Next question. What is the absorbance if radiant power is reduced to 50%? For this, we'll take the expression A is equal to log 1 by T. Absorbance is equal to log of 1 upon transmittance. It is expressed as log I naught upon I, where I naught is the intensity of incident radiation and I is the intensity of transmitted radiation. So incident radiation is 100. Transmitted radiation is reduced to 50%. This is log 2, which calculate as 0.301. So with the help of this expression, we can calculate the absorbance 0.301. Next, calculate the absorbance if the percent transmittance of a solution is 80%. Again, using the same expression, A is equal to log 1 by T. A equals to log I naught upon I, where I naught is 100 and transmitted radiation is 80. This calculates to be 0.097. So this is the simple questions on the basis of Beer-Lambert's law. Next is the instrumentation of the UV visible spectroscopy. For the UV visible spectroscopy, radiation source is monochromatic source, and for this, commonly tungsten bulb is used, hydrogen lamp is used, and commonly deuterium lamp is used. These are the common radiation source for UV visible spectroscopy. For gratings or for the monochromators used are the Comu prism is used. These are the monochromators used for the monochromatic light. or litroprism is used to create the or to generate the monochromatic source of light. Sample containers used are mainly cuvettes made up of glass or silica glass or quartz. Glass or quartz, these are the common materials used for making prism. For detection of signal, barrier layer cell is used, and another common detector is photomultiplier tube. These are the common detectors used. Is commonly known as PMT. For the recording system, recorder pen is used to record the spectrum. So these are the instrumentation used for UV visible spectroscopy. Some general applications of UV visible spectroscopy. This spectral technique is used for characterization of aromatic compounds, conjugation in molecules, It is also used to determine the unsaturation in the molecule. Determination of unsaturation in molecules. It is used to determine the impurity in the sample, impurity in compounds. For example, benzene is common impurity in cyclohexane sample. Presence of benzene as impurity in cyclohexane sample is determined at 255 nanometer. Presence of band in this region or at this wavelength shows the presence of benzene in the cyclohexane sample as impurity. UV visible spectroscopy is used to determine the concentration of unknown compound, determination of concentration of unknown compound, by using Beer-Lambert's law. Determine the concentration. With the help of UV visible spectroscopy, we can also determine molecular weight of compound, molecular weight of unknown compound, molecular weight determination by using the Beer-Lambert's law. We can also determine or we can also study the kinetics of chemical reaction. We can also study kinetics of chemical reaction by using UV visible spectroscope. So these are some general applications of UV visible spectroscopy. It is a very valuable tool to determine the impurity, molecular weight determination of compound, kinetics of chemical reaction, conjugation and unsaturation in the molecules. These are the references. Thank you, all of you.